you've noticed, I have trouble setting weather R. And so when I get excited or I talk really fast, sometimes I'll just drop R's. And people start doing it back.
Originally, I worked at a gas station, and there would be multiple customers that I would respond to them in their accent, and I would have to catch myself. Like there was this really nice Korean couple that would come in, but they had very thick accents. I would wish in the same accent, and they understood me. So I was like, I guess I'll just keep doing it.
People are such a shitheads lately. I got yelled at, not really yelled at, but they got really mad at me because I asked her if she had 9 gallons of water instead of, or I asked if she had 10 gallons instead of 9. Sorry. Just question, but just.
Like gallon jug.
Yeah. Because we have one of these little things you fill up.
I always wondered who are the type of people that put those water dispensers in their house. And okay, you live in a rural area, that makes sense.
Right.
Okay,
Well,
you
I don't
live in
wanna
the
see-
suburbs. What do you need water? Office.
Well, if you live in Ashland, I looked at the water breakdown, it's not good. There's a lot of lead and stuff in the water.
Well, have you been up to the reservoir? It's I mean, it's just a lake. I mean, it's a reservoir, but it's a lake.
In Ashland?
Yeah, but
Oh,
above,
yeah, you're talking about right next to the swimming hole.
above
Above the swimming hole, okay.
Albert Park. It's like a big, huge reservoir. Opens that one.
Well, we have a little filter in our faucet after we get the water. It's not good. There's lots of heavy metals. I'm like, this is why this is a high cancer rate in Ashland.
One of my mentors, he works for NASA. He's a contractor for NASA making spacesuit for the Artemis project. We were having like a super serious conversation about it.
The guy on that network, Josh, they gave me his dog's name. He was a boy dog. Or just male or female. He said, can you repeat it? And I'm like, that's not what I asked. He said, well, this is the name. I'm like, that's as he tell me. My cats are female. Their names are Aristotle and Socrates. I don't know what you want from me.
His name is Max. Oh, so he's a boy. No, how would you assume Max?
People often assume my cats are male. I don't care. I give them male names. That's unexpected. I thought it'd be funny to name one.
so with these cats.
Are
You
you?
are?
Yeah.
Oh.
I like cats too, I don't know. It's like,
They just want to kill you. Immune system.
yeah. I stayed over at my brother's house one time after a baby shower, so I could try home. And they had family over, so I slept on his couch, and they decided to put the cats in his house instead of the main house. I woke up and I couldn't breathe. I was like, oh shit. And I looked down and there's two cats sitting on my chest. I'm like, oh. But then I could feel the allergies kicking in too, so I was like, cats are weighing down my chest and now I can't breathe.
Oh, jeez.
Yeah, you're 5.
Cats?
Yeah.
Mm.
Girlfriend worked at the shelter.
That's the worst. I'm sorry. I knew a girl like that.
She fostered cats for a while. All of a sudden, like 6 of them.
I knew a girl that worked in society. And she would post on Facebook constantly about all the animals she brings home.
Yeah.
And I'm like, okay. That makes terrible.
Yeah, that many cats, no matter how many times you clean the litter boxes, they're gonna smell.
Keep it. It's a process.
Yeah, I bet.
I had a buddy that owned a cat. He lived in an apartment there, like, no. So he would put like his litter box in his closet, his baby's closet. I guess he let someone baby or cat sit. And for 2 weeks while he was gone, the cat was using the litter box. He was just peeing in the closet. So he came back and was just smelling like the cat.
That's the worst. Cat pee is impossible. Especially my cats never pee outside the box. When Aristotle, when she's mad at me, she'll shit outside the box, but never pee. It's really annoying.
This is the 6th. 22.
22 years old.
Yeah.
My cats are
In cat years? That was regular years.
That's regulated. Ancient.
old.
You sound like you're happy.
Happy, but relieved.
One more cat.
Because it has to be a real choice.
Yeah, because she's not black, she's tuxedo.
Long good tuxedo.
Yeah. She has long hair, but she never cops up.
Are we doing
The other one,
chapter
the other
67
one,
this week?
on the other
Yeah.
one, does, and she keeps everywhere every time. It's always on the carpet too.
Yeah.
I can't remember where to find it into chapters.
Oh,
Are they
I'll have
in
to post the link or,
Okay, are they, because I remember they were not in the textbook, right?
yeah, they're like
So-
online.
Oh, okay, is there a link that we could find?
Yeah,
Or we just gonna post them later?
I'll post it,
Okay,
yeah.
sounds good, thank you.
All right, let's get started. So I did grade your midterms, but then I decided not to hand them back because there's like a few people that haven't taken them, so I didn't want to start having them float around. So hopefully by Thursday, I'll feel comfortable giving them out. If you did want to look at them, we can, look at them individually. But I at least kind of wanted to talk about like the grading and the scoring and to kind of figure out your grade. And so I made an announcement about it. But essentially, right, the midterm had a nice average of a 60. And so what I did to calculate your average, so you can see your raw score. So I just took your multiple choice, which was 34 questions, and then weighted them times 2, so that gave me 68. And then I weighted the free response as 32 points, so that gave me a nice 100 there. So that was the weighting. And yeah, I kind of kept it that way just with how the free responses fell. They were a little all over the place. So that's also kind of the trick in trying to make the perfect test is with multiple choice, right? People can kind of guess, but then it's difficult to display your knowledge because you could also know something and pick the wrong answer. And so that's where the free response was trying to help that out. But obviously a free response test also can freak people out, and then you just get blank responses. And so with that, there was a pretty wide standard deviation. And so that was 16. And so then if you haven't taken statistics, especially with Kevin Murphy, I highly recommend it. But let's just give a quick rundown of statistics and where you want to be. And so when I'm looking at this grade, that means I'm probably going to center the average around a B or so. Again, it kind of depends. And as a science department, we don't do pluses or minuses. So keep that in mind with GPAs and panicking and all that. So we've already made that decision, so there's not going to be a plus-minus distinction. So then I'll probably center this around a B, and then you have to start calculating each standard deviation out. And so what that means is if you have a standard deviation of 16, and so let's go on the lower end, because that's usually what people are concerned about. So then, 44 would put you around a C average, again, roughly speaking, and this is just normalized distribution. Then second, you're at about a 28, so that's around a D. So again, you can kind of look at your scores. And that being said, there's nothing unsalvageable at this point. So, at least if you took the midterm, there's a grade, you can always improve on that score. And then, of course, you can calculate. And obviously, on the higher end, this could get skewed. So, an A is maybe looking around a 72-ish average, and then above that, you're probably in good shape. So that's kind of where the scores are, And then obviously there's other components to your grade. So the labs are a big portion, so just turning them in and completing them goes a long way. So that's the big reason why people don't pass my class is because they're missing half their labs or something. So again, some score is better than no score. And so again, you can kind of calculate that, see where you are. Again, if you're on the lower end, that's definitely just a reason, to study more and kind of figure out what went wrong. So that's why, again, I will hand out your exams hopefully by Thursday. And so if you are missing an exam, I don't see the person that I'm thinking of, because most people have confirmed with me that they've got their exams scheduled, but there are just one or two people that need to let me know ASAP when they've taken the midterm. Since, we don't have a testing center. Anyways, stop talking.
So to calculate our overall score, I guess would we use what you used with the multiple choice times 2 and then with the
Yeah, so your total score is in there as a separate column, so I added that. But then I don't know if you're trying to ask me where you kind of fit on this roughly.
how would you figure out how you fit on the scale?
Well, so that's the other caveat, right? Is like I don't know anyone's grade until the end, because what I do is I take all your points and then I normalize it again, so the same sort of thing where I take the average. So I'm just telling you, you can kind of calculate where you are midterm wise, right? And then you have to know, am I turning in my labs, right? Am I performing okay on them? And so the problem with the labs is they don't really allow much like standard deviation, like people usually just do well on them or they don't turn them in. So usually your grade distribution is determined by the midterm and final performance, typically. Does that make sense to everybody? And so you could, again, like attempt to calculate a weighted average, right? Because the syllabus tells you how much everything is going to be weighted. But what I'm telling you is at the end, right, everything will be averaged by the percentages. You'll have some sort of total score that gets normalized so that, you know, we fall on the curve. Because, right, a typical chemistry exam is about in like the 60s or 70s just for a score. Like that's pretty standard for chemistry. Like the ACS exam is like a 50% passing rate. So, and I did put ACS questions in there, so putting difficult questions.
What does ACS stand for?
American Chemical Society. It's like a standard. We don't do it here, but you could, like after the entire general chemistry series, take like the ACS standardized tests, and there's like certifications that go along with that. But just because we're a community college, we don't have the OChem portion, so we don't bother with that. And
Kind of like a bar exam.
I mean, not as rigorous, but I mean, kind of, but yeah, nowhere near the same standard. All right, so I think with that, we're ready to go into chapter 6. And so now we're really taking the idea of our valence electrons, right, our electronic structure that we've been looking at. And so now we're going to dive into, well, how do they bond? And so now let's look at our types of bonds. And so, of course, right, compounds are composed of atoms held together by chemical bonds. And so, most generally speaking, right, any sort of bond has to result from attractive forces, so some sort of, right, positive-negative interaction. And then really the question is, how polarized is this interaction, and then are they sharing electrons? So that distinguishes our bond types. And so we have 3 main types. So ionic, which we'll briefly summarize, so that is metal plus nonmetal, and that involves a transfer of electrons. And so again, right, we'll see that really discrete charge distribution. So we have cations and anions, right, coming together. And then we'll look at covalent bonding, and so those are typically nonmetals plus nonmetals, again, just generally speaking. And the big distinction is that they involve sharing of electrons. And so metallic bonding, we're going to save, I can't remember right now. I want to say it's the beginning of 2nd quarter. But generally, we'll call it a sea of electrons, so kind of these delocalized, excuse me, electrons. But again, let's revisit this topic. So we'll look at this later. All right, so now let's focus back on our 2 main general distinctions. So again, ionic versus covalent. And so the thing with ionic, and so we've established we can write our chemical formulas. The idea is we're making a neutral molecule here, again, balancing our charges. And so if we look at the ionic structure, it's this very distinct structure. So this is our crystal lattice. And so, of course, note that it's repeating units. And so we'll start to get into this chapter. So notice that we have our sodium cation, and it's going to be small. You can imagine, right, why that is. So it lost its valence electrons, and now it's going to be contracted. And again, thinking of that effective charge, but we'll look at the trends later in this chapter. And then, so note, right, our chlorine, the anion, much larger, so think about that. So it has an extra electron, so that's what makes it fatter. So again, compared to the number of protons, so it can't hang on to that extra proton as tightly. And then note, right, they're just repeating units over and over and over again, right? There's no bond between them. And so this starts to dictate, right, some of the properties of salt. So if you can think about trying to slice salt, well, that generally doesn't work very well, right? Because it's pretty brittle, so it just kind of fractures and breaks. And that's because of this, again, our molecular structure here. So thinking about trying to slice that, and it's all held together by charges, so then you get this weird brittle shattering effect when you do break it. So that attributes to its properties, and again, high melting then, because we have these repeating units. Yeah.
Oh, so when it comes to crystal structures, is the structure of the crystal affected more by the size difference between the atoms or the structure of the orbitals?
So that's going to be more size and packing. So we'll save crystal packing. I think for third quarter, we'll kind of look into like the typical packing structures. But right now, we're just appreciating that it's repeating units over and over again. Yeah, and so again, high melting point, so that's also attributed to this repeating crystal lattice structure, so very stable. And so if we compare that to a covalent bond, and so of course we're just looking at water here. And so these water molecules, right, they are sharing electrons. And so let's look at that actually. So we can start with our Lewis dot structure of oxygen, right? 6 valence electrons. So there it is. And then we compare it with hydrogen. And so it's Lewis dot structure. I might as well add a second one. And so what we can see is, right, how they start coming together. So we have, right, each electron going in to form a bond here. And we're using this little half arrow notation to signify single electron movement. And so then they could form. And so again, right now they're actually sharing electrons. So I have my single line here, so that signifies 2 electrons there. And we've just drawn it as a bond. I'll also add, so this is a normal bond, so that means, again, everybody is contributing 1 electron to the bond, so we will look at not normal bonds later. And so if we look at our covalent bond, and we can think about our melting points and kind of what dictates that. So right when we melt something, so we're not breaking any bonds, but we're disrupting these intermolecular forces between them. And so these structures, right, since they're only bonded with themselves, really, that makes these intermolecular forces a lot weaker compared to our crystal lattice ionic. And so that's why we see these lower melting points. And of course, right, that's kind of why water is then a liquid at just ambient temperature. And of course, you can give it, right, a little bit of heat, relatively speaking, and then it's steam. And then many of our other covalent compounds, right, share these similar properties of low boiling points, relatively speaking. So lower boiling points / melting points. All right, so looking at our ionic bond, so now we're going to look more in detail. So again, ionic involves a full transfer between our metals and our nonmetals. And so note, it's always your metal that tends to be supplying the electrons. And so it's going to be losing electrons to become the cation. All right, you can write the little t with a plus sign so you can remember, oh yeah, cation is positive. And then the nonmetal atom, so usually chlorine, sulfur, oxygen, right, is accepting that electron to become the anion. All right, so now we can start breaking down this process and kind of look at what happens. And so let's start with this process. So of course, right, we have sodium, and we could write the Lewis dot structure if we want it, or electron configuration. Yeah.
What was the third type of bond again? Ionic, covalent, and what?
Metallic. But that's just like when you have a metal, but like I said, we'll revisit that later. And so now, right, we can start breaking it down. So we're looking at our sodium, and so nice shiny sodium. So at some point, we'll play with this in lab. I haven't determined when I want to play with it. And so what's the electron configuration of sodium? So one valence electron. So what is it? Do you have the rest of the electron configuration?
No, it's neon 3s.
3s1. So perfect. All right, so we have our electron configuration. All right, this is telling us, okay, this is our valence electron. So, right, it's ready to give it up. And so we see that drawn out here in this little process. And so, of course, right, it's losing our electron, so it becomes a sodium cation. You could draw that Lewis dot structure as well. So sodium, then minus one electron, become our cation. And so meanwhile, we have chlorine. And so, of course, right, chlorine starts off as neutral and really a diatomic here. So what's the electron configuration for chlorine? Thank you. All right, so now we can see, and this is becoming, right, a little more obvious now. Okay, well now we have 7 valence electrons. So it's really close to having a complete octet, right? It just needs one more electron in that P. We could draw out just our neutral chlorine here. So 7 valence electrons. And then just, again, showing now an oversimplification of this process. So now plus 1 electron to give us our chlorine anion. So 8 electrons now, so happy. We could draw its new electron configuration. So 3s2, now it's 3p6. And so again, just to emphasize, okay, now it has a filled octet. Yeah.
So because the sodium is positive and the chlorine is negative, does that mean that it's polar like a magnet?
Yeah, essentially, right? So that's what dictates attractiveness, right, is any sort of polarity. Yeah.
Sodium loses electron, maybe positive.
Yeah, so right, recap, so now you can look at it, right? So you have sodium here, right? It had its one little electron, lost it, right? Then it got down to the neon electron configuration, so fulfilled octet there as well. And then, right, that means that formally speaking, that electron went to chlorine then. And so again, right, we can appreciate the properties. So I think we've kind of mentioned this before, how drastically different the properties are. So of course, right, sodium ignites in air. You would not want to eat that. That would be like burning on your tongue, reacting with your water. That wouldn't make sense. And then obviously like chlorine gas, again, toxic, corrosive, and combine the two for table salt. So So completely different properties.
What's the difference between an electron transfer and electron sharing?
I mean this, right? So where you have your electron actually leaving versus going back to the water one, right, where they are physically sharing. Yeah, Ben.
So, I'm just asking a clarifying question. So, for the transfer of electrons, is it the metal losing an electron and then transferring that to the non-metal?
Yeah.
Okay.
Yeah, so the metal, we're always going to see the metal is always giving up the electron. So that's always like the formality is usually assume, yeah, the metal is giving up electrons. And so, right, again, we're just emphasizing with our Lewis dot structure and both our electron configuration that we can see right where kind of the action is occurring. And so this is, of course, looking with potassium, right? We could make potassium chloride, so similar concept. And again, same thing. So we have our 4s1, so our one valence electron, and there's that tendency, again, to make that 1 plus ion there. Okay, we already looked at that. And so this is just a reminder of, right, our common charges. So hopefully your periodic table already has this, right? You should have a giant +1 for the first group, giant 2 plus for this group, 3 plus for group 3, and you have this weird 4 plus 4 minus switch, and then 3 minus 2 minus 1 minus. And so, of course, the other thing to note is, well, okay, if these ionic compounds, right, have cations and anion portions, then that means that they are conductive in solution. And so let's see. And so again, right, we have our basic unit is called our formula unit. And so it's just electrically neutral. But again, right, crystal lattice structure. So that's all that's emphasizing here is they're all just repeating units in that ratio, but again, not really bounded to one another.
What chapter of the textbook was?
6. And so again, right, they always contain positive and negative ions, and the sum of the charges has to equal the sum of the negative ions, so assuming that this is neutral. And again, right, it reflects your smallest whole number ratio.
Is it always a factor of 1 between the charges? If you have one that's 2 plus and one that's 2 minus?
Yeah, so it could be like that, so then you still have to balance it. And so the next page is, again, just more kind of typical charges, but it's kind of confusing. So you might want to highlight, so zinc is always typically 2 plus. And then for the purposes of Gen Chem, silver is always considered 1 plus as well. And I believe cadmium is another one of those. And then what's confusing, so these are, again, like the typical oxidation state. And it's pointing out that they all have this same electron configuration, so NS2, NP6, ND10. So just showing you why it's in these oxidation states. But confusingly, right, lead can also be 2 plus, tin can also be 2 plus, indium can be 1 plus, thallium can be 1 plus. So they do have different oxidation states as well. So just keep that in mind. And so now that's what it's showing down here, that, okay, now it has this electron configuration of filling in the s orbital. So let's look at that so we're a little more clear. So let's write the electron configuration. let's just start with neutral lead. Yeah. Oh, you have it?
Xenon,
Xenon.
and then 6s2, 4f14, 5d10, and then, sorry, I lost my place. And then 6p2.
All right. So we all started with that, right? And so then what it was just emphasizing, so again, now do it for lead 2 plus. So which electrons would go first?
The 2p orbitals.
So our p orbitals, and so that's good, right? So again, we're just kind of reflecting our orbitals. So yes, we would probably expect those to leave. And so again, that's what it was trying to say up here, that we still have our 6s2 included. Just kind of funny how it's worded. And then again, compare now. So now 4 plus. So which electrons do we expect to go next? Yep. Yep. And so now the 6s2 would go, right? We're not going to want to disturb those filled f orbitals or d orbitals. So yes, it would pull from the s there. And so again, we're kind of seeing how typically, right, the s and the p act as our valence electrons, especially, right, if these inner orbitals are all completely filled up, right? They're going to be pretty stable, so it's not going to be messing with that typically. Yeah.
Is the stability of an atom at all determined by how far it's been ionized?
I mean, yeah. But that's why you can only, ionize so far.
Also, I'd imagine after a while, you need so much energy to take the last few
Right.
back.
Yeah.
It wouldn't be worth it.
Yeah, so that's the other point. All right, so we'll keep looking at that. So let's do a little naming refresher so we're all on the same page with naming. And so we have, again, our ionic compounds. And we said, okay, well, that was a metal plus a non-metal. But now the trick here is that you have two types of metals. And so you have what I call our monovalent metals. So again, our metals that only form one type of ion. So meaning, right, we always know what oxidation state it's going to be in. And so that's obviously going to be, right, your alkaline metals, so group 1, group 2, and then those ones we pointed out. So zinc and aluminum, except aluminum we'll talk about, and silver. And then so anything else, so metals that form more than one type of ion, so I just call this multivalent metals. So meaning, again, right, they can take several oxidation states. And so with these, we're going to have to name them differently. And so the distinction, so let's remind ourselves. So I think we had done the simple kind of monovalent naming. So again, we could just name it. So if we were doing Na3P, so we state our cation, so sodium, and then change the ending to "ide", so then we have phosphide, right? And then we know how to rederive the formula back out, because again, we always know that sodium is 1 plus. We know that phosphorus has to be 3 minus, and I like using the swap trick because that's the easiest way to solve our algebra for x and y, to swap the variables, and so we get our formula back out.
What makes it a phosphide as opposed to a phosphate?
So phosphide is the atom, phosphate would be the polyatomic ion. And so then the distinction with these multivalent metals is that we can't just state our metal, we have to specify its oxidation state. So let's look at iron oxide and iron oxide. And so of course, right, how do we name these two? So we have FeO and Fe2O3. And so first we have to figure out the oxidation state of our metal. And we can do so based off of the anion. So what's the charge, the oxidation state of oxygen? So -2. And so what must be the charge then on this iron? 2. So 2 plus, so perfect. And so now all we have to do is name it. So iron 2 using Roman numerals, and then proceed with the rest, so oxide. So just naming our anion. And so now try this one. So what's the oxidation state of iron? So 3, and you could have, I like reverse swap tricking. So then if you reverse it, double check that this matches. Okay, -2 is the oxidation state of oxygen, that's correct. So that's probably 3, and then you can do math. So 3 times 2 is +6, -2 times 3, -6. Just double check ourselves. So now iron 3 oxide. So the only key is, again, right, that little Roman numeral to state the oxidation state. And so that is for our transition metals, and then those weird inner transition p-block metals that we mentioned, right? Thallium, lead, and a few others.
And aluminum is
Aluminum is
the exception, because it's always 3, right?
yeah,
Is
it's
that
always
metal-
3
metal
plus.
alloy?
Well, there's actually 2 exceptions with aluminum. So yes, aluminum is always 3 plus, but then what we find is aluminum actually makes covalent bonds, but we'll talk about that
Okay.
as we go through this. All right, so back to multivalent naming. And so like we saw, so now we can look at this iron sulfate example. And I think eventually I need to print you guys out a polyatomic sheet to help. And so that way you can just refer to your polyatomics. So I'll get that. And so again, right, we look at our iron sulfate. And so you would have to look up this sulfate and see that it has a -2 overall charge. So then you could determine, okay, this is iron 2 plus then, again, to have our electrically neutral compound.
So why do atoms form these polyions if they don't completely satisfy what it needs, like to build or to take from the electron shell?
So it depends like on geometry and other things. So we'll save the answer to your question probably, I think, third quarter. We'll kind of revisit this. Because long story short, it has to do with geometry and like where the d orbitals are. Because like, yes, it doesn't get quite to the full octet, but it can play around and make itself happy by doing other things with the d orbitals, essentially. But yeah, like I said, we'll keep diving into this. So as you can tell, right, that's kind of the theme of chemistry, is you can keep kind of diving deeper and deeper into things and keep applying things. But all right, and then, so then with this Fe2, SO4, 3, so again, reverse swap trick works nicely here. So again, you just have to verify that sulfate carries that -2 charge, and then that gives us iron 3 plus for this one. Does that make sense so far? how to determine oxidation state of your metals. And then, again, write your P block metals. So a lot of them are not multivalent, obviously, but it's just those weird ones. So lead, thallium, tin tend to be those typical ones. So those heavier analogs, as we're seeing. So indium probably. So all these guys I'd be suspicious of. Typically don't see antimony, but yeah, bismuth, lead, tin, all those have different oxidation states. And so again, we have our easier naming system where we just put it in parentheses. So again, right in parentheses is your oxidation state. And so don't get confused, right? So Cu2O, that's going to be copper 1 oxide versus copper 2 oxide, which is just CuO, balanced out. Yeah.
So do you ever see these metals like copper and iron with negative, they're not called oxidation states, they're called something else. But you see copper 1 and copper 2 here, but say instead of a positive ion, you got a negative ion?
Metals don't typically take negative ones.
Are there any that do?
I'm not that I can think of readily. You'd have to look at more esoteric research. But even then, I've never really seen metals in negative oxidation states. And I can't emphasize this enough that it's the charge of the cation, right, not how many. So that's usually where people go wrong. And this is a more historical reference now. And so you might see this on older bottles of chemicals, or if you're reading like an older paper, or even sometimes current papers. And so how they used to name it is there's typically two most common oxidation states. So if we're looking at iron, it's either typically iron 2 or 3. Again, that's most common. And so it was decided that the lower oxidation state takes the -ose ending and the higher takes the -ic. And so you might still see that. And of course, the problem with this naming system is it's very limited, and like we've mentioned, right, so it's not just limited to these oxidation states. You can have iron 1, iron 6, iron 4, and you can't reflect that in the naming. And so now, that's why we've moved away from this older system and gone to the Roman numerals, but you may still see this again. All right, so let's try some practice then. So see if we can look at the electron configuration of our transition metals. And so you might want to start with the neutral as well for some of these to help you, and then try to guess, right, where is it pulling the electrons from as it goes to these oxidation states.
So you said it usually doesn't pull from the D or P if they're full.
If they're full, yeah.
If they're not
But then
full,
these
would
are
it
going to,
take from the D over the X of the P?
so that's what you have to try to figure out, yeah. So let's at least look at palladium for a second, and then I'll let you think about iron some more. And so let's actually start with palladium's electron configuration, so just the neutral. And what do we predict for that one? Because that's actually a tricky one to begin with.
You can start with krypton,
So krypton,
5s2, I think 4d8.
and so I'm going to put, right, that this is kind of what we expect, right? Just kind of filling normally. But palladium's kind of funny. And it actually wants to fill up, right, the d orbital. So 4d10 is actually what it does. And so that's already unusual, right? So it's just starting off, since it would rather try to have a filled d orbital if it can. But either way, we still get the same prediction for its electron configuration. So what's our palladium 2+ electron configuration?
Krypton, 48.
So krypton, 48. And so then,
Would that make it more stable if it,
well,
in comparison to things around it, because it fills that d electron, that d shell?
so-
I'm asking about its behavior.
so you mean in this one? Or, so the problem is, right, we're having a little bit of oversimplified discussion.
Okay.
And so, right, it fills up this, so yes, that is true. But then the other thing is, so when it plucks off 2 electrons, however it goes, it's not going to be in this same degenerate energy level. So what I would predict, and I'm just kind of making this up, but this is based off of crystal splitting diagrams. And so I would predict it to take something like this configuration, right, where you have 2 orbitals that are higher in energy, and then this would actually correspond to an octahedral geometry. And so that goes into, like, yes, it is trying to make it stable, right? So then when it's losing 2 electrons, it's going to change its geometry too, right? So that's like the other thing that we're not getting into, but yeah, but it shifts those energy levels around and make it more favorable, again, depending on geometry.
So, for the first one that we did, we filled in the 5s2, and then we went to filled in the 48, but with the way that the energy levels in the orbits, it prefers to fill in that 4d10 first. When you remove those electrons, how come it doesn't kind of like, those electrons revert back to filling in the 5s2 and then the remaining of the 4d?
Yeah, I get what you're saying. It's just probably not invoking the s orbital because of the d geometry. And so again, right, we'd have to have like a little bit more detailed discussion. I just kind of threw in, again, based off of what I'm judging from that it lost 2 electrons, that it's probably an octahedral complex now. But to like fully confirm that, right, we'd have to confirm that, right, talk about whatever palladium complex we're talking about, and then, yeah, like draw its orbital diagram reflective of that geometry.
So it can jump so quickly between the 5s and the 4d because, as you were saying earlier, the higher the levels go, the less energy is between them.
Yeah, so they're already pretty close, so that's why things start to get fuzzy. And so again, that's why it doesn't even feel like we would expect it, right? So again, this goes back to on an exam, this is an acceptable answer because that's what we expect. but then trying to understand, right, how they really behave and react. So palladium is pretty stable because it's really acting like a 4010. And so, right, just kind of think about that if we look at their properties. So we have, nickel, palladium, platinum. So these are, nice metals, and they have good reactivity. And then what's even weirder, I mean, look at this on the P table. So nickel, they say fills 4s2, 3d8. Palladium, they put 4d10. And platinum is even different, where they put 1 in the S and then 9 in the D. So it's all just reflective of its potential reactivity too. And
So you mentioned at one point that, you mentioned at one point that the families generally have very similar properties, but gets a little weird when you get to the transition metals. Is this why?
yeah,
Okay.
yeah. And then what's even like weirder is that so back to this, sorry. So typically speaking, so why people like to use like platinum and palladium catalysts, like they're pretty famous, not just because they're expensive, but because the heavier metals tend to do like 2 electron transfers versus like nickel will just do 1 electron processes. And so that's not as favorable for catalysis, especially if you're trying to think of like, mimic multi-electron processes like sugar production, like getting into biological processes. All right, so now did you guys get a chance to look at iron for a second? I'll give people a minute or so. I heard mixed. Let's look at iron 2.
Are we going to be going into the properties, the properties of like metal alloys in this class or in a future semester?
No, that's in a completely different, that's like materials chemistry.
Okay.
So what do we get? Let's just start with the neutral iron electron configuration. What do we expect?
Argon, and then 4s2, 3d6.
4s2, 3d6. So I like that. I don't think you could really try to do any other permutations. But then I think this makes it clear kind of why iron has a 2+ oxidation state, right? So which electrons are probably going to go first? Yeah, the S. And so, okay, so then we have argon, and that leaves us with 3d6. But then can we imagine why 3+ is also favorable?
Would it be to take out like the 3s and then also 1 from the d orbital?
I would think that it would be 4s and then the 3d3 because that takes away all of the coupling to the neutron, to the proton.
Yeah, I mean, the s orbital is what goes first. But then, were you saying that it would lose the next one for the iron 3?
Yeah,
Like the d
exactly.
orbital?
Like the 3 pairs would go away.
Because then it would just have all unpaired electrons.
Yeah, so that would be favorable. So we have, 1, 2, 3, 4, 5, 6. And again, it's probably not in this geometry, so they're not degenerate anymore. I'm just kind of drawing it like this because we don't have any other information. And I'm not gonna make a prediction what geometry this might typically be, I'm not sure. But yeah. Then of course, 1 in every d orbital, so that is favorable. Does that make sense? Yeah.
I don't know if this is like a dumb question, but for the second part the first part we did for iron, is it possible that it would take one from the d orbital and then one from the s orbital, or?
I mean, that's a good theory. Yeah, I mean, it's not seen for the iron, but, you know, I would say be open to it maybe for other metals. Like, yeah, it's not out of the question completely.
Okay.
Yeah, it goes back to geometry arguments as well.
Is
All right.
there a dedicated class to the geometry of orbitals and electrons?
Yeah, so we'll touch on that a tiny bit, but that is the entire field of inorganic chemistry and then organometallic chemistry. And all right, so let's look at cobalt and chromium, and we'll go over them, and then I'll let you have a little break. Yeah.
So this is a little, it's related but unrelated to what we're discussing, when it, and kind of talks about what his question was with the metal alloys. Gold is often used in electronics for its like transfer of electricity. The properties, like when I look at it and I see the F14, 5d10, and then 6s1, is it that 6s orbital that kind of makes it a nice property for using it in electronics?
Yeah, I wouldn't know what dictates the property in electronics. That's,
Sure.
yeah. Gold's also just like really nice and stable.
And very malleable, right?
Yeah, so it's super soft too.
It's also in the same row as copper, which has used in electronics all the time.
All right, let's do, what do we have for cobalt's neutral?
It's argon,
Argon,
4s2, 4d7. Hopefully I counted the 7 right.
and then, oh, 3d7 though, right?
3, that's right. That's what always gets me. I forget to drop the d by now by 1.
All right, so this looks good. Do we all get this? And then, so cobalt 2 plus, what do we think is going to happen?
Would you say, generally in the transition metals that they want to build a D block, or is that just certain ones?
I mean, it's like, so it depends, right? Because you have to see like where it is, and then,
To filling them, then they're probably going to want.
yeah, so it is tricky, so that's why.
So for cobalt 2 plus, it would probably be argon, then 3d7.
Yeah, I mean, that's my prediction. So argon, so probably lose those. 3d7.
Why wouldn't it want to drop down to 3d5 and have the 2, the unpaired?
I'm not sure why it does it for this one, but, so what did you guys get for cobalt 3 plus though? Because that one, it does do funky stuff.
I put 4D4.
4S1 3D5.
So 4S1 3D5. So this would be my prediction. And so I think you were trying to go for that idea up here. Typically speaking, I'm not really sure why that happens, but it just will like lose those S electrons, together. So that gives us our 2 plus oxidation state. But then, yeah, for this one, so if we had put, again, right, our kind of expected here,
Maybe, is it
argon 3d6.
Is it easier to lose the 4S because it's a higher energy level, so it's further away from the nucleus, maybe?
Well, it's also like, again, how it can fill it. So it's happier. So, right, if we compare kind of what we expect, so we have our 4S is empty, and then our Ds, so 1, 2, 3, 4, 5. And then, so again, kind of from our expected, so nothing in the S, and we have 5 filled, and then we have 1 paired, right? So we mentioned that whole energy price. And so that's why it's always like, how much energy is being paid to pair them versus how much is it to put it in another energy level, right? So that's why it's always kind of hard to predict, but that's why this is actually what we see where it goes 1 in the 4s1, and then where you can have each D just having 1 electron.
Oh, because it's less energy, right? Because you don't have 2 pairs.
Yeah.
Okay, that makes sense.
And so this one, like, it could be like a geometry argument again over why it goes to the 3D7 and doesn't do something else. So that's always like the deeper answer is geometry. But.
So if we did put down the argon 3d6 on the exam, it would be accepted?
Well, probably I'd have to like word the question more elegantly, like say something like, oh, this is the expected one, why is it not this, like that sort of thing, like,
Can you go up to the iron example real quick?
And that's why this one, right, you could have made the argument, well, maybe, why didn't it go to the 4s1? I'm not really sure. Like, it goes back to geometry, what it typically makes. It's not always a clear cut.
When you talk about the geometry, you're talking about like the orbitals and the shape that they take when they're filling like the...
Yeah, so the problem is, right, again, we don't have a full picture, so we don't just have like iron 2 plus typically. It's like going to be in some shape, connected to some things. And so that's the information that we're missing. Yeah.
So the number of neutrons in an atom's nucleus affect its orbital or its energy level?
No, not really. It just makes it heavier mass. So yeah, isotopes are good for like labeling experiments and doing all sorts of other things with chemistry, but. Oh, and then let's do chromium before we forget about chromium. So what do we get for chromium? So argon, so octet rule. So that looks good. So we could look at other things for chromium. So chromium is a weird one. So what's its electron configuration normally?
Argon, and then 4s2 and 3d4.
Argon. I would make another prediction. So you said 4s2, 3d4, but what might it actually be? What do you notice?
Would it want to take from the p orbital to the other p orbital? Yeah.
Not the p, but the.
Oh, from the 4s to.
Yeah. Yeah, so this is another weird one where it goes 4S1 and then it wants to fill those Ds. So again, it's just one away. But then goes to chromium 6. And then we could predict other oxidation states too, so I didn't put it up here. But so chromium 2+ though, so that of course just goes argon 3D4 again. So that's kind of, just note that. And then chromium 3+, then it just would lose another one. So 3D3. All right, that's probably a good place to take a little 10-minute break. So we'll be back here at 12:10 roughly.
The lab we did last week, it's okay if we turn that in on Thursday, right?
Yeah.
Okay, thank you, and also clarifying. So the reason it's like 4S, it wants it to be closer to the D finishing, and wants it
Yeah,
to be
like I'd
closer.
rather like put one electron in every D, or like what it's trying to do is like, it's almost considering that the 4S and the 3D, since they're so close, that they're almost all degenerate. So then it's like, oh, well, how can I spread out, these electrons evenly among these 6? But
Okay.
yeah, that's why it's always like a tricky judgment call because they're so close. And yeah, are they, filled? Are they pairing? Are they not pairing? It's a lot of
Thank you.
considerations.
I think they say that after the age of 30, only 15% of males ever fully spread. So it's like you did very important. Like when last did you see your dad run?
Been a while.
Remember we just got a contract with Farming Forestry
Oh, yeah?
for blocking and piling like 20 over the Grand Circuit Creek.
Oh, yeah.
He has my dad acting as a crew boss for the first one. Just manager for all the sorties. It's like my dad will work in the forest really good. He gets home, he goes over stuff. Because he's gotta replace this stuff.
I know you're probably inundated with a lot of test score questions. When I was listening to the live of you going over the scale, so I saw that you put the A 472 and then B at 60. So if
Yeah.
you scored, the total score of your midterm was like 63, then that would throw you into that B range.
Yeah.
If you scored like 72, it'd be more right on that like A
Yeah,
range.
exactly. So you can, and again, that's just like where your midterm lies, so then it depends on your overall grades. If you're doing, well in labs and everything, obviously that puts you higher end.
When I looked at the total on my score, it was 74, and I was like, that just cool, great.
Yeah.
Okay, thanks.
Have you curved it yet? It hasn't curved yet.
Well,
you
I
said.
don't do any curving till the end.
Okay, that's good to know. So my
Yeah.
grade will, okay.
Yeah, so your grade is completely inaccurate till basically.
The end, okay. I have some questions for you, that kind of random one. But how far did you get through chemistry? Did you get like a master's? or a-
PhD.
Really? What was your favorite class?
I mean, I guess like inorganic chemistry, because that's my spec.
That was your specialty? Okay.
Yeah.
How does inorganic compare to organic? Is that less carbon-based? Because organic's all
Yeah.
carbon-based,
Yeah.
right? Okay.
Yeah, except I was more like organometallic, which basically means I know enough OChem to like make a simple molecule, and then I throw metals at it and make it do cool stuff, or try to. That's the
Those are
long
my
one.
questions. I know personal. I was curious.
Yeah, the temperature one was very.
Yeah.
What was your experience getting a PhD? Because I might end up having to get one because physics you can't really do much with.
Yeah. No, it's just a long journey.
Yeah.
Yeah, you just like can't give up because like people will just give up in grad school.
Right. So just keep going.
Yeah, so if you like throwing yourself against the wall daily, you'll be fine.
Cool. Thanks.
Actually, a lot of people there. A lot of nice work.
Yeah. Is Dusty too?
Cool. I think so.
We'll have to talk to him.
Actually, I think he has a master's. Kevin Nuts. Or something. Crazy. Worked as a contractor.
I know that. Wasn't Doug Gardner an engineer?
Yeah. He's a structural.
That explains why all of his trig values were engineer based. Yeah.
This is how you make a truss.
I think at one point he said like he didn't like theory, he liked it to make sense, like with a physical aspect.
I think he has an engineering skill. He'll draw plans for people to use. And the science department.
I took intro to poetry and my teacher had a PhD too. And he always made jokes about how it's I don't remember his name. Brown hair, yeah. Bigger dude, really friendly.
I thought of it this morning, right?
Really?
No, I haven't. Small world.
I remember when you cracked a joke like, it didn't take well, and I was like,
I'm funny.
don't worry guys, it's just a movie. And he's like, yeah, it's a movie. Well, I want to see what he's got. What do you say?
It always feels like, A, it's none of your business, and B, fuck you, whatever I want. I had a friend who like,
All right, did we make it back from break?
yeah, excuse me, I am a human with my own autonomy, I can vote for what.
So the last part of chapter 6 is just going over our atomic radii trends and the corresponding cations or anions. And so like we kind of mentioned earlier, right, our cation radius is smaller than, of course, the neutral. So we can think about that, right? You have, of course, your positive nucleus in the center, and then obviously if you lose an electron, now you can pull those remaining electrons in tighter. So again, you can kind of appreciate this. So our lithium cation is has a much smaller radius, right, of 60, and this is in picometers versus 152 for our neutral lithium. And so again, just appreciate that. Oh yes, they are tiny. They're contracting a lot. So we can appreciate that. So of course, again, right, our 2+, our 3+. So again, we expect those, to be pretty contracted.
So you're saying the greater the charge of the cation, the more contracted the atomic radius will be?
Yeah, typically. And that goes back to, I feel like that should have been, where was it? Maybe it's in the next, I could be thinking about the next chapter already.
Is that true for anions as well?
So then anions are larger, right? They have the opposite effect. And so again, right, think about it. Okay, we have our protons in the center, but now we have too many electrons, right? So you're adding them, so now it can't hold on to them as tightly, so it's much larger. So our anions are always larger. So, whatever you need to do, circle that, star that. And again, just appreciate how they get bigger. So we go from 73 to 140 with oxygen. So not quite as dramatic with fluorine, but still almost doubling. So same thing with sulfur.
That has to do with repulsion from the positively charged center.
Well, and the fact that it can't pull it in, right? Because you only have, so if we go to the case of oxygen, right, we have 8 protons on oxygen, but then now we have 10 electrons, so that it can't hold on to those extra 2 electrons as tight. And so, again, our radius gets smaller, or larger. Radius gets larger. And so again, as we travel across the periodic table, then of course our charge, since it's isoelectronic, meaning same number of electrons, then we see our anions, again, getting a little smaller. And this is just a nice visual of that. So again, just comparing the neutral versus some of their cations, or at least representative ones. Kind of fun picture. All right, so now let's get into a few other periodic trends and how they relate to things. And so now we can talk about electron affinity. So has anyone ever heard of electron affinity, that term? Yeah, Trinity, you have? So what's electron affinity?
I do not remember. They went over it last year in my chemistry class.
And then, does anybody think of something that might be similar to electron affinity? Have y'all heard of electronegativity, though? There's some yeses. So I want to talk about both of them because they're similar but different, and it's good to at least know the distinction, especially now. And so most people, again, if you've taken some kind of chemistry course before, you may have heard of this term, electronegativity. And so in general, here's our periodic table. And so everybody always knows, okay, fluorine is considered the most electronegative. But wait, what are we actually measuring when we're talking about this? And so electronegativity, what it measures is basically how much an atom pulls and this is in a bond, though. And, this does give us a nice idea. We'll come back to electronegativity. We'll use it to talk about polarity. But what the distinction is electron affinity actually gives us more of the formal reaction of this. And then we're only looking at our atom individually, and this is calculated or performed experimentally. in the gas phase. And then, so with electron affinity, we can write it as this equation, right? So don't confuse it with your ionization energy. So it's basically the opposite of ionization energy as well, right? So instead of trying to remove an electron, we're asking how favorable is it to throw an electron on there? And so again, that's best summarized by this equation. So our metal, so just, our neutral atom that we're starting with, plus 1 electron is going to obviously give us our anion, and then plus this EA, right? So then it's asking how much is that energy? So is it favorable, not favorable? And so if it's exothermic, it'll be negative. And then we might also find that it could also be endothermic and be not favorable, right, and take energy. Yeah.
So is this idea directly linked, for example, with fluorine, why it's so reactive? I think it's considered to be among the most reactive halogens.
Yeah, so that's kind of the idea. And so let's kind of get there. And so that's part of it. So fluorine has a lot of reasons why it's reactive. It's also small. And so let's talk about its size. And so kind of what you notice too. So who has the greatest electron affinity here? Chlorine. And so this is a little odd in some sense because, right, well, we just said, well, fluorine is the most electronegative, right? In a bond, it's pulling the most. What kind of accounts for this discrepancy? And it's really a size argument. And so again, both are favorable, right? So let's at least point that out. So obviously, right, our halogens, they all have these negative energies. So again, negative is exothermic, so it's releasing energy. So that's a favorable process. But we see that chlorine, again, has at least the lowest, so right, the more exothermic. So great electron affinity, great meaning that it's exothermic, so it's most exothermically favorable. And so why this is, it's a size argument. And so again, right, fluorine is going to be smaller versus chlorine, obviously, because chlorine is 1 below, so it has an extra onion ring layer. And so typically speaking, larger atoms are better at stabilizing that charge. And so I would expect that that is why chlorine is, again, formally more exothermic. That it's probably just a little bit larger, even though, again, fluorine has those other arguments where it wants to fulfill the octet. Again, right, going back to those electronegativity properties, but just mathematically, that larger size of chlorine is going to stabilize that negative charge better. And so that's really the only little oddity in this. And then, of course, we can appreciate, okay, our alkali metals, a little bit higher in energy, still exothermic. But then if we go over to our group 2, right, those are actually pretty unfavorable. So they are positive, so endothermic reactions, so you would have to force them into those conditions. So not really favorable. And again, right, this is just reflecting our trends. So again, we know these have -1 oxidation states, -2, so right, they're going to want to gain electrons versus anything that's trying to lose them. All right, any questions on that one? Does that kind of make sense? Especially the distinction. So again, right, electronegativity is measuring that in a bond, though, so different calculation.
I have a semi-related question. Is that why gases like chlorine and fluorine are considered to be so dangerous because they're so reactive? So you breathe them in and they react with the water or whatever in your system? Or
Yeah, I mean, that's part of it, too.
biochemistry
And
question.
also, like, it also depends on, like, the state, too. So, like, obviously something that's in a gaseous state tends to react, like, faster.
Okay.
Yeah. And, like, right, you can think back to even, it seemed kind of silly almost, right, mixing those dry ingredients, the calcium chloride and the sodium bicarbonate, right? You're just staring at two powders. But that's part of chemistry, right, is that it does matter what state it's in. So yeah, being gaseous also means it's going to react a lot faster. And obviously, right, that does lead to the other properties of why it's so dangerous. And then obviously it is dangerous and reactive.
Do the natural abundances and the isotopes kind of play into that factor of what we were talking about just before with the electron affinity?
No, they just, yeah, they're more just for masses, and it's useful for other things like mass spec and doing like different NMR techniques to like look at your molecule in other ways, but yeah, not really like reactivity. And so again, right, we're just trying to appreciate how to understand chemistry. So obviously every model will have some limitation. And again, right, we've been kind of seeing with our Lewis thought structures, we've been seeing the positions of our ions in our crystal are critical to the stability. And so, right, we'll get more into this a little bit, but we're just kind of seeing, right, that repeating lattice structure. So that's showing us, again, right, the properties. And so again, right, we mentioned, okay, well, that starts to dictate some of those properties that we notice. That, right, it uses this word moving ions in and out of position, right? But again, you can see that that would be silly, right? Like you cannot move that ion because the whole thing would explode because they're all in this, right, alternating pattern. So again, that's why we get this. They're relatively hard. Again, you can think about trying to slice some salt and how silly that would be and how difficult. And that's why that is. And then, so again, it mentions these repulsive forces. So I'd assume that translates again to our macroscopic observation of it being brittle. And so again, right, okay, they're brittle, they shatter. Again, we can kind of predict that. And then we're getting into, okay, well, they are locked in position. And so yes, as a solid, right, they do not conduct electricity. So this would just be, right, like a pile of salt. So that would not conduct electricity, but rather, right, they need to flow somewhere. And so this starts to get into, well, an aqueous solution would conduct electricity, since then, right, they can separate into their cation and anion parts, and then they have physical motion in the water, right? So the water's obviously moving around at a molecular level, so then that means our sodium and chlorine can move around and then conduct electricity. Versus, right, a pile of salt where everything's just sitting there in their static positions. And so yes, now we get into liquid state, and if you wanted to go down the rabbit hole, right, this goes into ionic liquids and batteries and blah, blah, blah. That's a whole research topic. And so we'll see this at some point in lab, that a liquid ionic compound, so basically salt dissolved in water, will conduct electricity and lights up the light bulb. All right, so then, oh, this is what I was thinking of. So now we also want to get into calculating the energetics of our crystal lattice. And so, okay, we're again thinking about all the different forces. And so again, this crystal lattice structure is known as being very favorable and stable. And so, right, we have energy that comes in that is released from the formation of a structure. And so we want to quantify this. And so we're getting to that. And so, okay, now we can start to break down our process. And so now we can see, okay, well, what is our sodium losing an electron? So what is that? So, right, that's related to our ionization energy. So, right, remembering what that was. So, okay, how much energy does that take, right, for sodium to give up an electron? And so just appreciate, okay, we're given that our change in enthalpy for this reaction is 496 kilojoules per mole. So the positive sign telling us, right, that it's endothermic, meaning that we had to put energy into the system. And then, and we could put this picture back over here, right? Because we're just breaking down this process now. So we're saying, okay, mathematically, right, that was part of it, sodium losing an electron. And then, okay, if we go back to this little diagram, well, chlorine, right, we said had to gain an electron. Well, now we just learned what that is mathematically, so we can quantify that, right? So that's the same thing as its electron affinity. And okay, so then again, looking at for one equivalence of chlorine, and so we have an exothermic process here. So losing negative 349 kilojoules per mole. And so now here's a trick. So here's where the lattice energy comes into play. So it says, okay, well, if we're looking at this, right, well, our ionization energy of the metal is larger than the electron affinity. So therefore, right, to form our ionic compound, just adding these two numbers together, right, this is showing an endothermic process. But then this actually doesn't make sense, right? So we find, well, actually the heat of formation of most ionic compounds is an exothermic process and large. And so it's asking, right, why is that? So basically what this is saying, right, if we were to calculate this, so we have, right, so this is just our reaction now, so sodium, metal, so notice the state, right, so it's solid, so we're adding our sodium elemental form plus our chlorine gas, again in its elemental form, chlorine 2, to form our sodium chloride. And so it says, right, that the energy of this entire process is negative 411. And so what this is saying is, right, if there's no other forces, these two numbers added up should equal that. But it doesn't. And so now it's asking, well, where is the extra stability coming from? And the answer to that is, of course, our lattice energy. Right, so that is, again, that stability that comes into play once it's all surrounded in its nice crystal lattice structure. And so this is also exothermic, so this is formally saying, okay, this is the energy released when, right, these solid crystals form from separate ions. So kind of showing, it's trying to show what it's saying, right? So just imagine we have all these sodium chloride ions floating around in our gaseous state, then boom, measure the energy that's, in this case, right, released when it comes together. So if heat is being emitted, right, that's telling you that's favorable, so exothermic process to, again, put those crystal lattice structure together. And so, right, we can then kind of measure it. So like we were looking at, right, we can figure out how much our crystal lattice energy is from figuring out this difference. Or you could calculate it roughly from our sizes. Oh, sorry. And so now we get to our formula, which I think I've been talking about this in vague terms, but now we're actually putting numbers and units on it and looking at it in the context of our two ions here. So now we're looking at, right, two ions, such as an ionic compound. And so we're given our formula here. So our Coulombic energy is equal to 231 attajoules per picometer. So, right, this is looking at something on an atomic level. And so that means this little distance here, right, is according to this unit in picometers. So if you look up, you know, this factor somewhere else or another reference, right, it may have different units on there. So just watch for that. So again, this is attajoules, picometers, so that means our energy is going to be given in attajoules. Picometer is going to be canceled out, right, with this distance factor.
Is that a constant, the 231?
Yeah, so this is our Coulombic energy, right, for, again, our two ions. And so a little bit of a simplification of our lattice energy, but now we can at least calculate this. And so let's just do sodium chloride, since we've been talking about that. And so we have sodium plus, chlorine minus, yeah.
So Q1 and Q2 are charges, are they measured in attajoules as well?
So we're just going off our primary charge. So Q will be like 1 if it's sodium, right? -1 for chlorine, and then.
Is it measured in attajoules?
Yeah, so it's related to the scale. So right, the energy is going to come out in attajoules, yeah. And then so the only tricky part is going to be this distance. And so just from previous years, you may have different answers, like depending on where you reference your text. So for this purpose, oops, where'd it go? I'm going to try to look at our size here, right? And you want to go, and so this is our radii, so we can add our two radii together. And so I'm looking at my sodium radii, right, our plus the cation one, so 95, and then plus, and let me find my chloride, so 181. And so that would be an appropriate distance. So again, right, whatever value you can find, but you want to find it for the size of the charges. But I'm not sure, your book might have slightly different values, or if you look at another chart, it might be different.
Q1 and Q2 is just 1 and -1?
Yep.
I got 0, which just makes the whole thing.
No, you multiply it.
Multiply, that's why.
Yeah, so multiply. And so, right, of course, you can see increasing magnitude, and that changes that.
Doesn't that end up giving you attajoules cubed?
I don't know what these charges are, just their primary charges. So I'm saying that the final answer is attajoules, not these.
The unit list.
Yes, they're just charges. So then we have 1 plus, 1 minus, times 231 and attajoules picometers over our 276. And again, right, there could be slightly different numbers for the radius. Now 231 divided by 276, since that's all 1. And so we have about, and negative, since I have my charge there, so negative 0.837 attajoules.
So, it being positive means that that's not right.
Well, it's always going to be negative, right? And it should be favorable, this energy coming together, because you're always going to have opposite charges. But then that's also what it's saying, right? Like this is a favorable attraction, right? So that's why it has a negative energy. So going back to this visual, right? Because we're kind of trying to calculate that, but it's really an oversimplification of what we're doing. So we're saying, right, what is the energy of this process? So, you know, we had just a sodium atom floating around, right, a chlorine anion floating around, and then what's the energy, right, they're in the gaseous phase, what's the energy of them coming together? And that's, again, based off of those attractive charges. So then that's the Coulombic attraction that we're calculating. Does that make sense? So let's do a little practice with magnesium fluoride at least. So try that.
How do we know the distance between the atoms?
You'll have to look at your book, so I can pull it up. So let's see, magnesium, looks like it's 65, and fluorine, 136. So total distance of 201, it looks like, at least, again, with the numbers that I'm pulling. And again, if you actually look up the compound and like figure out the distance between them, that could give you a different answer as well. So just, again, keep that in mind. That's okay.
And then for charges, you use total, so use 2 and -2, right? Or do you just use the 1?
You do, yeah, the one, so like the magnitude, yeah. So it sounded like everybody was piecing that together. So 2 minus -1, so just again take those absolute charges. So 231. So 2, -1. I already forgot my distance. There we go.
Is there any consideration for the 2 fluoride atoms?
No, we're just calculating, yeah, the 1. Because, again, that's right, the limitation of this equation, right, is that it's only 2 points. So, yeah, that being said, right, again, if we wanted our lattice energy, our true lattice energy, you'd want to take the difference of this if you had all this information. Otherwise, we're just, again, calculating our Coulombic attraction between 2 points. So then let's see what we got. So we'll make it negative. So did we get negative 2.3 attajoules? Double check my math.
So would you say that's a much more exothermic reaction than the sodium chloride? Is the number?
Well, yeah, so you got this sense, so we'd have to analyze, right, the whole reaction, but yes, right, the Coulombic attraction is going to be greater, right, than our sodium chloride. And so that's just, right, our general trend. So if something has a greater charge, more Coulombic attraction, so greater force, which gives us, right, more exothermic value. But then, of course, right, to get the overall energy, it goes back to, right, we would have to calculate the ionization energy for magnesium, the electron affinity of fluoride, and then add all that up. So yeah, we don't have the full picture necessarily of who's more stable, right, until we add all those other factors in.
Coulombic energy is describing the reaction between the
Yeah, well, it's just describing like the, yeah, so like the attractive force then, so then, yeah, it's also the same as like, yes, how favorable is that for those two to come together and sit at that distance?
And how does that relate to lattice energy?
It's basically our oversimplification of lattice energy, right? Since lattice energy, you'd have to try to calculate it as like a single point surrounded by all these other points that are like stabilizing it. So it gets a little bit more complicated, but we can at least, right, get a general idea from that charge, how big the charge separation is.
Does that equation only work for compounds of two elements?
Well, we're really just measuring, right, 2-point charges.
Okay.
So yeah, we're just looking at 2 points, right? So back to the magnesium fluoride, even though there's 2 fluorides, we just looked at the charge difference between a magnesium and a fluoride.
And the distance, that's distance from what? To plugging to
So the distance would be like,
from each other.
yeah, from each other, which we've been oversimplifying as just one radius plus another radius. So again, if you look up like an actual crystal structure, then you might have a different answer.
So would this only work for crystal structures? Because distance would become very variable if it was a gas, right?
Well, actually, like they do keep like they're pretty much the same distance, but the problem is visualizing it, right? So in the gas phase, we don't necessarily like know what it is, but the thing is with like a crystal structure, you have it frozen essentially in the solid phase, and then you can literally measure the distance.
Oh, okay.
Yeah. So this is just, right, kind of giving you an idea. So, okay, we have magnesium fluoride, but again, we're just calculating the Coulombic attraction of like these 2 points, right? And then, of course, right, notice magnesium fluoride is repeating units, so magnesium are fluorines, magnesium fluorines, right? So it's kind of funky. Okay, we'll start chapter 7, and by start chapter 7, I mean finish Coulombic. So see if you can try this example. Do we get an answer for our lithium and fluoride Coulombic attraction? We have 1 plus, 1 minus. What do we get for the radius? So 209, is that what other people got? On my notes, I have 136 plus 60. It's like 196 maybe. Is that what other people got? So somewhere around there, I might go with 196. I think I pulled that. And so then we can calculate it. So 231 divided by 196, and times our, oh, no, that's correct. So then we have, right, negative 1.18 added joules, right, of Coulombic energy. And so what about this next one? Did you get to it at all? What do we need to look at? What processes is it asking about?
You need to find the electron affinity
Of which one?
of this reaction.
So,
Between the two atoms, and then,
so who's gaining the electron, though? Because remember, electron affinity is saying how much energy requires to add an electron.
should be fluorine.
So yeah, so then that's half the process. So fluorine plus our one electron to give us F minus, and we'd have to look at that. So I think I have on my notes that it's negative 500 or negative 0.545 added joules. I gotta have to look in your textbook for that. And then what else will we need to look up? What's the other half?
The lattice energy.
So not the lattice, because that's essentially what we had up here, but what? The lithium energy, so like ionization. So adding, so taking lithium, and then how much energy does it take to remove an electron? Right, and so there's our process. And so again, just to emphasize, right, we need to track our electrons. So we are losing or gaining an electron with fluoride, right? And so that means, right, lithium has to be giving it up. So there's our electrons, so balanced process. And then according to my notes, I have this as 0.86 added joules. You'd have to look this up. I think it's in your book. I'm just curious if I Google ionization energy of lithium. Of course, trying to find it in added joules. So Google does say that it's 0.86. So should be able to find that reference information. And so then, right, we could continue to calculate it. So again, right, we could add up these two numbers and figure out what our remaining factor is. Since, of course, right, this is showing that this would be an endothermic process, right? Our ionization energy is larger than our electron affinity. So somewhere our Coulombic attraction comes into play. All right, that's a good stopping point. So we'll pick up on Thursday with covalent bonds. So we'll look at that and start practicing a little bit of structures. And then, oh, we will do a quiz. So the quiz will be probably on chapter 5 stuff, again, like practicing those formulas, wavelength, energy, all that Rydberg stuff.
You know what I was
I have another question
Yeah, I forgot
for
to
you.
look
Why
through
do
the-
some
the
elements
radius
just
on the-
not want to exist? Like the heavier ones that we
Right.
discovered, and then elements like francium, they have such a fast decay rate. Like what?
So that is more dictated by their neutrons, but then the thing is, like, we as scientists are not really sure, like, why some of them are really unstable and some are not, like, it has to,
Uranium, for example, is quite stable.
yeah, so it's like, it's some weird combination of like, oh, this certain number in mass is stable, but then, you know, you add one more neutron and next thing you know, it's radioactive, like, yeah, we don't quite fully understand it all, but.
Thank you.
Yeah, that's where the neutrons come into play, is like the isotopic stability.
In the textbook, where would we be able to find the radius? Like in the
It should be there. Let's see, because I'm thinking it should be in chapter 6 somewhere. Okay, here's a chart. This is page, what page is this? 183. And it has the radius.
is this like will this like all of the future problems like revolve
Oh,
around this?
Yeah, so either it's gonna be pulled, like if homework, you have to look at like a book, but on an exam, if I was gonna make you calculate this, I'd have to have some like charts of something, or, yeah.
Sweet, thank you.
Yeah, but otherwise for the homework, you're kind of forced to hunt around in the book.
Thank you. Chapter 6. My one last question is, would you mind if we scroll down a little bit?
Oh,
I just
yeah.
have one question for you. So I understand that. I was curious, where did this equation come from?
So that's just our ionization energy. I can't remember if that was chapter 4 or 5 when we talked about it, but that's just saying, right, remember when we had to, ionization energy is just how much it takes, right, to remove that electron or each subsequent one. So that's all that is, yeah.
Thank you.
Yeah.
So me, Amy, and Bonnie are probably gonna be coming in on Thursday to redo our lab.
Okay.
Because me and Amy have work today.
Okay,
We don't on Thursday.
okay, that works.
Is there gonna be space for us to?
Yeah, or we'll make space, if, yeah. All right, have a good day. Any other questions online before I end this stream?
On the multiple choice, I got a 20 out of 34, but on the free response, I didn't do good.
All right, thanks again. I'm going to end this stream. Have a good one.